Hello everyone. So today I'll be presenting this paper of PointCloud pre-training with natural 3D structures. The reason why I'm trying to introduce this paper is because the idea was very creative. So I thought maybe this could give you guys some insights to apply to your own use. So contents will be like this. So there's been increasing demand of 3D object recognition technologies in real world applications with PointCloud data. For example, it is frequently utilized in mobile robots and field of self-driving cars. However, there are lacks of large-scale PointCloud datasets, unlike 2D computer vision field. Also, there's a huge difficulty in annotating 3D data, which is therefore labor-intensive. So the authors came up with this very interesting idea, which was that learning fractal geometry could improve learning representations of real-world 3D patterns more than conventional 3D datasets. So what is fractal? Fractal here refers to a type of geometry that is self-similar at different scales, meaning there are complex geometric shapes that exhibit similar patterns at different levels of magnification. And they are often found in natural structures such as trees, coastlines, and clouds, like this images here. So overall, the authors of this paper propose using fractal geometry to learn a representation of real-world 3D patterns. So plus, they thought of the recent trend of studies, which was a pre-training method. So they wanted to somehow create large-scale fractal geometry and pre-train existing point cloud network with those data set. So consequently, with careful experiments and thorough verifications, they managed to come up with these two major solutions. Number one was PC-Fractal Database. It is automatically constructed 3D point cloud scene datasets that they believe somehow could represent natural 3D structures. Number two is formula-driven supervised learning, aka FDSL. It means that they created a system that can generate infinitely many data sample and target label pair with a mathematical formula that mimics natural representation of real world. So now let's dive in to see how the PC fractal database was made. And this is the overview of the whole process. Let's briefly look into it step by step. First of all, the authors explained that they use a 3D iterative function system, 3D IFS, to automatically generate 3D fractal models. And 3D IFS goes like this. First, they made random n number of affine transformations, TJ, which is nothing but a 4x4 matrices, with elements of it being uniformly sampled. And it has value between -1 to 1. Then, starting from an origin point, they iteratively apply these affine transforms to it. They selected each TJ with probability of absolute determinant of TJ over the sum of all of absolute determinant TJ. So doing this first and second step n number of times, you get 3D fractal model. And the paper done it 4,000 iterations. So now that we made this one 3D fractal model, we have to annotate it. We need to assign it a category. So to do that, they first divide the range of variances observed in the data set into a fixed number of beans. They then assign each fractal model to a bean that corresponds to its variance. Then they perform a quality check on each bean by computing the average distance between all pairs of fractal models within the bean. So if this bean distance is below a certain threshold, they consider the bean to be valid and assign it as a category. Otherwise, they merge it with a JSON bean until a valid category is obtained. So why are they doing this? Because by binning the fractal models by variance, they aim to ensure that each category contains fractal models that are similar to each other inside a category, and at the same time distinct from those in other categories. So now that we categorize each models, we need to make our dataset actually large enough for pre-training. So for that, we use these fractal noise mix. And the augmentation starts with first selecting one model as a fixed major category and take 80% of points out of it. Then with all the other models from different categories, here we call them minor categories, take 20% from each of them. And lastly, fill 80% of major category model with all different 20% of minor model. So now what we've got is models with all different 20% of minor models. And all those models are categorized into major category. And they say that this is to keep important fractal shape feature maintained, because just giving random point cloud to augment would cause to lose that fractal information. And lastly, it's time we generate a scene with all the models we created. First, multiple random objects are sampled. And second, bounding boxes for each fractal models are assigned and goes through a sequence of transformations for better representation of natural world, for example, like scale, rotation, and translation. And then finally, all these process models are placed in non-overlapping positions. Then done. These are the final results after going through every step we've been through. So the experiment part, to verify that this somewhat mind-blowing approach actually works, they've conducted thorough experiments on, I think, every possible way. And I thought I should learn such kind of complete quality check when suggesting a new method. But for the sake of time, I'll introduce only these key block parts that I think is the part they argued as their main contribution, and leave the rest for you guys to have a look if you are interested. So to evaluate the effectiveness of 3D fractal scene dataset, they compared pre-training performance between regular CAD model, which is basically what ModelNet is, and fractal models. And table 4 here shows detection result of VoltNet, pre-trained with PC-Fractal database, outperforms ModelNet pre-trained VoltNet to 0.5% and 3% respectively for ScanNet version 2 and Sun RGBD.
I'm kind of lost in the middle, so before you go further, I have a couple of questions. Yeah.
Yes.
So first of all, how do you determine the number of categories like M? M is the number of categories, right?
Yes, yes.
So how do you determine the number?
Actually, they conducted a experiment on this what number of categories will be best to perform, outperform than other methods. But as I said just before, I didn't introduce it because of it, I thought I will be in short of time. So yes, it was decided by experiment.
Okay, so they tried a different number and then determine the best one.
Yes, that's right.
Okay, and then you first come up with the affine transformation and then sample it with different probability with the equation that is given there. And then how is it related to a fractal? So you have this affine transformation, and then how do you convert it into a 3D fractal model?
So there is the origin point, and you apply affine transform TJ, and then there's transformed points by TJ. So there are 2 points. And then that transform point is also affine transform by another TJ. And they keep like multiply like that, and you get 4,000 points.
So
which consists of,
so you have affine transformation, and then you have 3D fractal model. How are they related? So do you apply affine transformation to the fractal model, or the other way around, or how are they related?
So affine transforms used in this IFS, 3D IFS is fixed. So there are n number of affine transformations, and so they could be sampled multiple times, same affine transformations. So it could randomly represent some repetitive shape naturally. So the affine transformations, the sequence of affine transformations applied to the origin, starting from origin point, is itself, I don't know, making a fractal geometry. So if you see the results that I've reproduced in maybe in the behind slides, I suppose maybe you could
So I mean, usually when you say 3D fractal model, it has different equations that generates the unique fractal form. So maybe they correspond to the each category of fractal models. So here from this explanation, I feel like if you just simply apply this affine transformation with an iteration, it will converge to some 3D fractal model. So without actually using 3D fractal model specific equation. So this part is, I'm a bit confused with this part.
As I understand, I think the transformation is used to create the 3D fractal model from the certain point, since it's iteratively applied from the initial point, and then you get the second point, which has different location from the initial point, and then with those 2 points, you apply the transform again, and you move on to some kind of other place. Then you would get a 1, 2, 3, 4 points, and then apply, you then add 8 points, and then on and on and on. And then in some number of iterations, you would get some kind of certain, point cloud of fractal geometry. So it's how they created to use it, as I further understood. Am I correct?
Yeah, so that part is a bit confusing part. So usually, I mean, when you say 3D fractal model, it has a specific equation that generates the, if you apply this equation iteratively, then you will create the fractal geometry. But then from this explanation, it seems like Xian says, if you just simply apply this linear transformation over and over, it will generate a fractal geometry. So I wanted to make sure that if that is actually true.
As far as I reproduce my the paper's result.
So you try to implement this?
Yes.
Okay, so when you iteratively apply this affine transformation with this probability, it actually produced a 3D fractal geometry.
Yes, actually, not this much, I don't know, sophisticated, but somehow I got a
okay,
shape. You can say it's fractal.
Yeah, but so, in this case, not only one specific geometry, but in later slide, we have different categories. That means you have a different shape of vectors. So then how do you create all this variation from this affine transformation? I just
So after you first applied this 3D IFS, I suppose maybe there are not much variations, but when you do this fractal noise mix method, you apply this one. I guess this is the real step that that increases the variety of models.
Okay. So I have one last question. In the most recent slide, the later the part that you're explaining. So the fractal usually represent or simulate the natural phenomenon, natural scene, like you give the explanation. It's like a ocean or like tree structure, such. And in this case, it compares the fractal model with the CAD model. CAD model in this case is not natural scene; it's an actual object. So how I'm wondering how they compared, how fractal model can be compared with this man-made object model.
For that part, I also wonder how can they are related with like indoor scene data sets like ScanNet version 2 and SonRGBT, and also compared to ModelNet, which is Professor also mentioned, is an object, man-made object, artificial object. But unfortunately, they didn't just explicitly mention the relation. They just showed that this works and we'll prove it by experiments like this. So yes, there are no actual explanation how that fractal geometry, which represents natural scene, natural landscapes, can help represent this kind of man-made objects or indoor scenes. So
okay.
So I might in my thought, when you do this kind of task or experiment, usually what they do is that they use a, how could I say it? They use this made data set to pre-train the network first. And then after that, since this model has been trained to like look into some 3D information, they use that pre-trained model and fine-tune to a specific task. In this case, I guess that will be ScanNet v2 and SonRGBT to do like object detection or 3D segmentation, I guess, PointCloud segmentation. And so I think they're just basically measuring whether this training scheme or the made data set are a good good data set that could be trained well as a good backbone to be initialized. So I think that's what they are doing now. So does that make sense?
yes, that's right.
Yeah, so I guess, yeah, just basically so the first version will be just naively random initializing and train on ScanNet, and the option they are proposing is that using their data set, first train it in the fractal data set and fine tune using the ScanNet data set.
So thank you for your comment. Shall I move on? Okay. So to move on, next, after they obtained optimal parameters for PC-Fractal database, which is, for example, like variance threshold selection, and the number of instances, categories, and scenes and objects. They've found out the best parameters for this. And they showed this comparison of existing self-supervised methods like random rooms, point contrast, CSC with PC-Fractal database. And the backbone network option here is whether PointNet++ or SRUNet. And for mean average precision score with IU threshold 0.25, we can see that PointNet++ pre-trained on PC-Fractal database shows the highest result for both fine-tuned dataset, ScanNet version 2 and SonRGB-D. However, for mean average precision threshold with 0.5, CSC method with SRUNet backbone network showed highest result. So what they did was to stack a bunch of PointNet++ models and let the number of parameters match that of SRUNet, and they didn't mention how exactly they stacked up. Anyways, it turned out they got highest result not only with threshold 0.5, but also with 0.25 with this stacked model. And lastly, they also showed that how PC-Fractal database pre-training method shows effectiveness with limited amount of fine-tuned dataset. So PC-Fractal here shows considerably superior performance over methods such as CSC, point contrast, and the model trained from scratch. So what really notable things to see is that the smaller the data set for fine-tuning is, and the better the result of PC-Fractal database than other pre-training methods. And now, what are limitations? First, the authors only evaluated their method on 2 datasets, which is indoor datasets, ScanNet version 2 and SonRGB-D. While these are commonly used datasets for evaluating 3D object detection methods, could be beneficial to evaluate the proposed method of more diverse and challenging datasets to demonstrate the generalizability. And second, the authors only considered 3D object detection tasks in this paper and did not explore other applications such as segmentation or classification. Also tried to reproduce the results, but then there were total of 9,720,000 models in the data set. And I didn't know it take total 8 days to create data set and then pre-train them on backbone models. And it was even with 4 Tesla version 4 for V100 GPU. So I couldn't reproduce the actual fine-tuned result, but instead I created a small data set of 10 model instances per 10 categories for test and visualize some of them for your better understanding. Yes. And finally, I wanted to share my random idea just came up to my mind. So one is to create large scale data set for pre-training and facial expression or facial features. Maybe you could figure out and define a universal representation, shape, or geometry that represents the facial features or expression like fractal geometries on every possible 2D or 3D facial inputs, such as real anime 3D characters or 3D stylized characters' faces. And with large-scale pre-trained model on large-scale dataset, which learn universal representation of faces, it could be used to do various kinds of downstream tasks, or even maybe in 0-shot or few-shot settings. Yes. And that's all. Thank you for your attention. Thank you for listening. Any questions?
So how do you pre-train this network?
You mean their parameter setup, or the
I mean, like, how do you train it in terms of like losses, I guess. Like what will be like the loss function when you pre-train the backbone model?
Actually, I didn't quite looked into it in detail, but they used VoltNet as their backbone model, so maybe they followed the VoltNet architecture and their loss function, I suppose. So, yes.
So is it VOLT net? Volt?
Yes, VOLTE net.
Oh, okay. Okay, thank you.